And I'd like you, when you write your unit test, don't just do one input, one output, because that's kind of not really awesome. One of the main things we're testing here is, can you handle multi-dimensional space, right? So it'd be great if your unit test had 20 inputs and 33 outputs, or something like that, just to prove that you can. And it should work for arbitrary. It's no more work to code for n-dimensional space than it is to code for 2-dimensional space. So it should just work, in theory. And how much is differed by too much? Well, it depends on how you parameterize your unit test, but if you understand it, you can usually get a feel for if you're right or not.
It also depends on the magnitude of the noise compared to Y.
Yeah. I like to always draw noise from a Gaussian distribution. I'll explain why later in the class. I think I'm going to not do that today. But if you choose a Gaussian distribution with a deviation really, really close to 0, then you can be rest assured your model parameters should come out exactly right. And then if you crank that up and see that it doesn't affect things, then you know you're in good shape.
What about the mean compared to Y? Should it be much smaller than Y, or?
Where are we looking at?
Number 4.
Number 4. Add a little random noise to Y. Oh, what is the mean of the Gaussian noise?
Yeah.
Always 0. If you're adding anything other than 0 to it, that's going to throw off every single point. They're all going to be shifted towards the mean, right? So, yeah, when I say random Gaussian noise, I mean the mean is always 0. The deviation is whatever you pick. Yeah. And, well, I mean, wouldn't it be fun if you could add huge amount of noise and the thing still ends up being pretty accurate? Because that would mean, hey, I have a really robust linear model. And that's what I'm kind of hoping to get you to see. This is a really darn robust model. It should be able to handle quite a bit of noise and still get it pretty close to the original model. Should be able to penetrate your noise if you have a reasonable size training data. Is that a fair answer? Okay. I want to walk through a numerical example of OLS, because I think a few people are just struggling with that. That's what I want to do next. Anybody else have a question you want me to answer first? Yes?
Okay in our code if we just happen to just use random sources of uniform distribution of noise?
Absolutely. When I said I use Gaussian noise, I meant I use Gaussian noise. When I explain why, you'll realize I'm correct and you'll want to use Gaussian noise too. Until then, I wouldn't expect you to be converted yet. So how about that? Yeah, if you add any kind of noise, it should be fine. You do want it to be centered at 0, though. If you pick a random number between 2 and 7, and you add that to all of your points, do you see what will happen is, on average, you're adding 4.5 to all of your points, which is basically going to shift them. So you'd expect your final model to be shifted by 4.5 off of what you had originally produced for your model. Okay. Let's do an example of OLS. Now, the first thing I want to show you is this. What is OLS do, ordinary least squares, and what does activate do? These are kind of the two components you're coding up in this assignment, right? Let's put it this way. For activate, what goes in is X and weights. And the output is Y with a little hat over it. Right? Okay. Here's what goes into OLS. The input is X1, Y1, X2, Y2, bunch of training data. And the output is going to be M and B. Right? In other words, the purpose of ordinary least squares is to train your model. We're going to find all the parameters that we need, and we're going to find those parameters by giving it a bunch of example X and Y's. The purpose of the activate function is, given X, what is Y? Now, let me ask this question. If we have to have a bunch of X and Y's in order to train the model, what good is the model if it can only compute Y, which we already knew when we trained the model? Just checking to see if you've even got the point here. Does anyone answer that question?
Predict new data, like
Yeah, can predict new data. This might be X that was not in your training data. So for example, if I pick everyone in this room and I ask, what's your height? What's your gender? How much did you enjoy the movie Titanic when you last watched it on a scale of 1 to 3? And finally, do you like pineapple on your pizzas? Yes or no? If I ask these questions to all of you, and then I pulled a random person into the room from out in the hallway, and then I asked, what's your height? What's your hair color? How much did you enjoy the movie Titanic when you last watched it? Then I'd go do a bunch of math. I could compute whether or not this person likes pineapples on their pizza. And would it be right? It depends on whether or not that can be computed based on those values that I measured. To the extent they're correlated, yes. To the extent they're not, no. Do you think there's any correlation there? I bet you there's some. I don't bet it's strong, but I bet you, whether or not you like Titanic and whether or not you enjoy sweet things on a pizza, there's got to be some overlap there. I don't know. One thing that recently hit the news, there's an article out there, you can Google for it and you'll find it. People were using deep learning techniques to analyze people's faces and determine whether or not they were gay. Now, that's really controversial. Nobody likes that idea, right? Because you like to think that what's in my head is only in my head and not on my face, right? It's really disturbing when a camera can look at you and say, Democrat, Republican, anarchist, traitor, or whatever else you may be thinking inside of your head. But there are subtle little correlations, and given enough features, the more things you actually have to compute by, the more you can actually start to tell what's going on. In the example of this housing data, the things we're looking at are, none of these features are really the price of the home. But given all of these different values that describe the home, you can get a pretty accurate estimate of how much the home is worth. And that's kind of the first step into getting into this. So, do you get activate? We've done an example of that. We've got a unit test of it. X goes in, you multiply it by a matrix, you add it to the bias, you get the output. Is everybody clear on that? Okay. I'm guessing OLS is a little less clear. Let's do the example.
The meaning of the weight in the instruction is different.
The meaning of the, oh,
Because you said
that's one thing I need to talk about. Yeah. Let's talk about weights here. This is one weird thing about my instructions. I ask you in your activate function to have a vector of weights and an input named X. I give you weights all in one vector instead of giving you a matrix named M and a vector named B. And that's weird, right? Why am I doing that? This is a case where I'm asking you to trust me. It'll make a lot more sense in the next few assignments. But suffice it to say, you would pass in an M and a B here if the goal of this project were linear regression. Because in our next assignment, we're going to have multi-layered models that involve a whole bunch of layers, you get to the point where you'd have an arbitrary number of M's and an arbitrary number of B's, and just keeping track of it all gets to be a pain. And so we tend to glob them all together into a great big vector. So one of your jobs will be to take these numbers, kind of separate them apart into a matrix and a vector, and then use M and B and X to compute Y. Did you catch that? Okay. Does the bias come first or does the matrix come first? Turns out it doesn't matter. Here's why. You control the activate function. You also control the OLS function, which produces that weight matrix. So as long as you're consistent, it doesn't matter how you interpret it. You can have the bias come first and then the slope, or you can have the slope come first and then the bias. It's still the same equation. Okay. Let's do OLS. Let's suppose we have some data. We'll have some, let's see. I think I'll do this mostly in text mode. So I'll just fill that up. We're going to have some features. and some labels. Let's suppose our features look like this. 0, 1, let's do 0, 1, and that maps to 2. And how about 1, 2 maps to the label vector of 0, and how about 2, 0 maps to the label vector of 1. There's some data, right? I mean, you can't argue with that. It is data. I picked 3 training patterns. Why did I pick 3? Because notice I have 2 features. And if I have 2 features and 1 label, that's a 3-dimensional space, and it takes exactly 3 points to perfectly constrain it. I'm trying to perfectly constrain my model so it'll be easy to test. So, reasonable starting point. You with me? Okay. The first step in OLS, well, the first thing you should do is probably get the instructions in front of you. So, let's go section 5.1 of the book. Ordinary least squares. And we'll scroll down to here. Okay. Your goal, should you choose to accept, and you do choose to accept, or else you will be forced to drop, is to implement these functions. So, in fact, that would be really convenient to have that in front of me. So I'm going to take a screenshot, copy that to my clipboard, come in here and paste it right there. Okay. First thing I need to do is, you see how there's a bunch of subtracting the means from all of these things? I'm going to compute the centroids of all of my vectors. So, centroids. What's the centroid of the features? I'm claiming it's 1, 1. Do you agree with that? Why is it 1? Because 0 plus 1 plus 2 divided by 3 is 1. And 1 plus 2 plus 0 divided by 3 is 1. And what's the centroid of the labels? It's the vector of size 1, a vector of 1. That's a pretty lame centroid. Do I need to mess with my numbers to get a better one, or do you get centroids? Centroids are a pretty simple concept. We'll leave it alone. Okay. Now, just for convenience, I'm going to take all of my data and subtract out the centroid. My new data looks like this. Minus 1, comma 0 maps to 1. 0, comma 1 maps to minus 1. And 1, comma minus 1 maps to 0. See where I got that? I just subtracted my centroids. Okay, I'll call this origin-centered data, meaning this data is now centered about the origin. The mean of it is the origin, something like that. Okay. Now, looking at these equations, what would we do next? I think we need to sum these products. Now, if you look at the equation, these products have to be outer product, and I'll tell you why. Let's see. Well, oh, whoa, where'd it go? There it is. Look right here. How big is y? It's however, well, in this case it's 1. And how big is x? 2. Has 2 elements in it. Can you multiply 1 by 2? Oh, darn, you can. Doesn't actually cause a problem. But, well, it depends how you arrange them. What if y were 7 and x were 13? Can you multiply a vector of size 13 by a vector of size 7? Wait, you can't do a 1 times a 2 either. Dot product does not work with 2 vectors unless they're exactly the same size, right? Therefore, this must be outer product. So when you looked at this equation, if it looked confusing to you, that's because you were thinking the wrong thing. It wasn't dot product. It must have been, it wasn't inner product. It was outer product. Okay, do you know how to compute an outer product? just in case you don't, let's do an example. Let's suppose we have two vectors, 1, 2, 3, and 1, 2, 3. What is the outer product of those? What you do is you transpose this one, and you put it down there like that. And then you do 1 times 1 to get this element, and you do 1 times 2 to get that element, and 1 times 3 to get that element, and 2 times 2 to get that element, and 3 times 3 to get that element. And basically the answer is 1, 2, 3, 2, 4, 6, 3, 6, 9. Right? Okay, now you know outer product. Okay. So we're going to have a great big fraction here. And the first, I don't know why it's red, first thing in this fraction is going to be y minus y hat, that's this one, right? Times x minus, and not hat, x minus x bar is this. So this times that. What is the outer product of 1 and minus 1 comma 0? It's basically going to be minus 1 comma 0. You with me? Okay. Plus the next one. What is the outer product of negative 1 and 0 comma 1? Do you agree it's going to be 0 comma minus 1? And what is the outer product of 0 and 1 comma minus 1? It's going to be 0 comma 0. Okay. This is our numerator. And then our denominator, that red is bothering me, so I'm going to change it to black. Whoa, that changed everything to black. There we go. Our denominator is actually going to be a bunch of matrices, because this is going to be the outer product of x with itself. What's the outer product of minus 1 comma 0 with itself? I'm going to claim it's 1, 0, 0, 0. Is that correct? I'll draw a box to indicate that it's a matrix. That will be plus. What's the outer product of 0, 1 with itself? It's going to be 0 times 0 is a 0. 1 times 0 is a 0. 0 times 1 is a 0. And 1 times 1 is a 1. Right? Okay, that plus. Finally, the last one. Aren't you glad I didn't do more than 3 data points? This would have been a big pain. What is the outer product of 1 minus 1 with itself? Because I'm computing this part of the equation over here, right? Okay. That's going to be 1 minus 1 minus 1, 1. Okay. Now I'm going to claim that this is all equal to some fraction. That fraction is going to be, what is the sum of these 3 vectors? Minus 1 and minus 1. So we've got a minus 1 comma minus 1 vector on the top. It's a little bigger than we need. And on the bottom we get the sum of those 3 matrices. What's that going to be? I'm getting a 2 here, minus 1 there, minus 1 here, and 2. Right? Draw another box just so we got that. Okay. Now how the heck do we take a vector and divide it by a matrix? Turns out there's no such thing as division in linear algebra. And by no such thing, I mean there is such thing. What you do is you invert the matrix and then you multiply, which is kind of what division is, right? You invert the value and then multiply. How are we going to invert this matrix?